Well, to get started in Sylvius, I'm going to open the brainstem cross-sectional atlas and select all structures. And let's begin at the lumbar level of the spinal cord. So I've just selected the lumbar cord, and what I'd like to highlight for you is the dorsal column. So here we have the dorsal column, and as I select it, the label that appears is the gracile tract. No cuneate tract, right? Because we are in the lumbar cord and we are below the level of the input from the arms, obviously. So the only axons we find here in the dorsal column are those that are serving mechanosensory signals from the lower body, the lower extremities primarily. So if we now proceed to section higher up in the spinal cord, you'll notice that we are adding axons to the peripheral sides of this dorsal column region. So there are some unlabeled axons that are out here laterally. So that's where we're going to find the cuneate tract, right? So the gracile tract medial for the lower extremity, the cuneate tract lateral for the upper extremity. So these are elements of our dorsal column medial lemniscal system, conveying mechanosensory signals from the spinal cord all the way on up to the caudal medulla. Now, before we get there, let's go back down to the lumbar cord and let's consider the spinal cerebellar pathways. So there may be afferents from muscle spindles and Golgi tendon organs and the like, or deep proprioceptors entering this dorsal root entry zone and entering the dorsal column. But as we ascend in the dorsal column system to the thoracic cord, some of these afferents are going to dive into the intermediate gray matter in a region that is on the medial side of this gray matter, and right about in this area we have what we call Clark's nucleus, or the dorsal nucleus of Clark. This is the origin of the axons that then sweep out and run from thoracic cord into the cerebellum in a pathway that we call the dorsal spinal cerebellar tract. So there's the dorsal spinal cerebellar tract. Now, an important point that I want to emphasize: the dorsal spinal cerebellar tract is on the same side of the spinal cord as the entering afferent fiber. So this allows us to establish an ipsilateral input to the cerebellum from the body concerning proprioceptive signals. Now, we've been emphasizing that in the cerebral hemisphere, the principle is contralateral representation. But I warned you that when it comes to the cerebellum, we have a different principle. It's ipsilateral representation. And this is how it's established via an ipsilateral dorsal spinal cerebellar tract that's relaying information derived from the same side of the body. In this case, the lower part of the body. Now, what about the proprioceptive signals for the cerebellum from the upper part of the body? Well, here we are in the cervical cord. Those signals are going to enter through the dorsal root entry zone and enter the dorsal column in the region of the cuneate fasciculus. And from there, these signals are going to ascend. Let me just select the cuneate tract so you can see what will happen there. They will ascend into the caudal medulla. So here we are in the region of the caudal medulla, and we are now very close to where we would find our full complement of dorsal column nuclei, including this far lateral external cuneate nucleus. So here's our external cuneate nucleus, and I'll highlight it here on the right side of this image to be consistent with where we started. So this external cuneate nucleus that's in view here received input from the ipsilateral afferents concerning proprioceptions of the upper extremity. From here, this external cuneate nucleus is going to grow axons that will join up with those that are running right next to it from the dorsal spinal cerebellar tract. And eventually, we can follow that tract all the way into the cerebellum. And at some point, this tract begins to accumulate axons from the brainstem that are serving other purposes, and for that reason we no longer call it simply the dorsal spinal cerebellar tract, but rather we now begin to call it the inferior cerebellar peduncle. and that peduncle makes its way into the cerebellum, which is where we are now. Okay, now let's return to the dorsal columns of the spinal cord and consider again what happens in the dorsal column medial lemniscal pathway. Okay, so we sort of jumped ahead a little bit to the spinocerebellar pathway. Let's get back to the dorsal column medial lemniscal pathway. So here we have a tracts, the cuneate tract and the gracile tract, that are going to ascend in the dorsal column region of the spinal cord until they hit the caudal medulla. And what will happen is that a nucleus will be encountered essentially on top of this column of white matter. There's a gracile nucleus sitting on top of the gracile tract and a cuneate nucleus sitting on top of the cuneate tract. And if we look a few millimeters above, now we can see that the nucleus is engulfed by the surrounding axons of the tract. So this is where we would find our second order neurons of our dorsal column medial lemniscal system. Okay, so we have tract and nucleus. Tract and nucleus. Now, these second order neurons grow out axons that are going to cross the midline and form a critical pathway of the brainstem called the medial lemniscus. Now, as these axons grow out, we call them internal arcuate fibers, but once they cross the midline, they begin to coalesce into a medial ribbon of white matter, and that's what medial lemniscus means, medial ribbon. So now we can follow this medial lemniscus all the way up the brainstem. Here we are through the medulla, and at this level, the medial lemniscus is in the anterior and posterior axis of the brainstem. But as we rise through the pons, the anterior part of the medial lemniscus begins to move out laterally. It's as if this medial ribbon is beginning to twist. And as it twists, while we rise superiorly through the pons and enter the midbrain, this pathway is now getting in a position to hit the ventral posterior complex of the thalamus that we'll find in the next section in our atlas. So here's our ventral posterior lateral nucleus of the thalamus, and it's in a position ready to receive the input from the medial lemniscus that we saw just in the previous section. Okay, and from the ventral posterior lateral nucleus of the thalamus grows the axons that enter the internal capsule and then make their way to the postcentral gyrus, allowing for the third order neuron then to relay its signals to the level of cerebral processing in the cortex. Okay, now let's complete our journey through the brainstem for mechanosensory processing by thinking about the signals derived from the face. And for that, we need to get into the pons at the level of the trigeminal nerve. So here are the nerve roots of the trigeminal nerve. So the mechanosensory signals of the first order axons enter the brainstem through the nerve root where they encounter a nucleus. So here's the chief sensory nucleus of the trigeminal complex. And from here, there is a outgrowth of a second order axon that sweeps across the midline and ends up being very close to the medial edge of the medial lemniscus. So somewhere around in here is where we expect to find the fibers of the trigeminal lemniscus. So I'm just going to select the medial lemniscus as a placeholder so that you know that there are some afferents concerning mechanosensation in the face near the medial edge of that pathway. And then as we ascend through the brainstem on our way to the thalamus, that medial edge of the medial lemniscus is now in a position to meet the medial division of the ventral posterior complex. We call that the ventral posterior medial nucleus. So here's our home for our third order neuron. This is where its cell body resides, and it grows axons that join the internal capsule and project to the inferior third of the postcentral gyrus. All right, now you may be wondering, how can I possibly learn all of this information and keep this straight? Well, there is really one key strategy that I would suggest, and that is to draw. I don't care how you draw. You can draw in the dirt if you like. But I would encourage you to draw and to make your drawings as large as possible. The bigger the better when it comes to making visible your knowledge. And as you draw, you can hold yourself accountable to what you actually see from your own hand. So what you produce is what you can then interrogate. And here's how you might go about interrogating your drawings. Let's imagine that you select the left medial lemniscus. Okay, so I'm placing my cursor here on the left medial lemniscus. You might ask yourself questions like this. Where are the cell bodies that grew these axons? Or you might ask, where are the synapses of these axons? Now, I'm going to encourage you to hold yourself accountable to the precision of your language. It's my conviction and my experience that precise language is a reflection of precise thinking, and that's what I want for you, precise thinking. Okay, in answer to the first question, where are the cell bodies that grew these axons? The best answer would be in the contralateral dorsal column nuclei. If we're talking about axons that are in the dorsal part of the medial lemniscus, we might say, well, those axons were grown by the contralateral cuneate nucleus. So if this is the left medial lemniscus, the axons in this position were grown by the right cuneate nucleus. If we're talking about the more anterior or ventral part of the medial lemniscus, those axons were grown by the contralateral gracile nucleus. Or for this left medial lemniscus, I'm referring to the right gracile nucleus. So yes, indeed, there is somatotopy in the medial lemniscus, with the upper extremity represented more to the dorsal and eventually the medial aspect of the medial ribbon of white matter, and then the lower extremity represented on the more anterior or ventral side, and eventually the lateral side as we end up ascending through the brainstem. So out lateral is where we would find the axons grown from the contralateral gracile nucleus, and more medial, the contralateral cuneate nucleus. And then right along the medial edge here at this point, we would find the axons grown by the contralateral, or in this case the right-sided, principal or chief sensory nucleus of the trigeminal. Okay, I hope that all makes good sense to you. Now, what about our synapse question? Where are the locations of the synapses of this left medial lemniscus? Well, the synapses would be in the ipsilateral ventral posterior lateral nucleus. Okay, why did I say ipsilateral? Because my reference here was the left medial lemniscus. I'm asking, where does the left medial lemniscus terminate? The left medial lemniscus terminates in the left ventral posterior lateral nucleus of the thalamus. And one way to speak of that would be to say ipsilateral VPL. Now, some of you may have thought, okay, where does the medial lemniscus terminate? You might have thought, all right, it terminates in the ipsilateral postcentral gyrus. Well, if you're thinking about where does the information ultimately go, it goes to the left postcentral gyrus. But that wasn't the question. I didn't ask you where the information went. I asked you, where do these axons terminate? So please keep in mind that I'm referring to the anatomy here. And the anatomy has a clear endpoint. In this case, these axons physically terminate in the thalamus. They do not project through the internal capsule into the postcentral gyrus. That's the job of the third order neuron, the thalamic neuron. Okay, I hope I'm clear about that. I know some of you will struggle to catch on to this, but the best way to grasp these concepts is to rehearse them, to practice them. So please make drawings however you can. Please explain them to your friends and family. I would love to see you do that. In fact, what I'd like to do now is pause and show you one such example that is out there on a YouTube home that does just that, explains the dorsal column medial lemniscus to friends and family, and now to all of you. So let's take just a minute and view this.
Hi, I'm Christy. This is my extra credit project for Neuro, Av20540977 with Professor Stein. Something you should know about me is that I'm not musical, I don't write songs, and I'm not a poet. but I do want extra credit, so I'll give it a try. I composed 2 songs about the different tracks that we learned about, and they are both set to children's tunes, so hopefully they will be familiar to you. This first one is about the DCML tract, and to orient you, let me show you that this is a finger, this is the dull end of a safety pin, and this says touch. So we'll be discussing the touch of the dull end of a safety pin on the finger, and the magical journey that it takes, sending the information all the way up to the post-central gyrus. So let's get started with the DCML tract, which is set to the tune of none other than the Itsy Bitsy Spider. Alright. The DCML tract can be confusing. The UEs are lateral, fasciculus cuneatus. The LEs are more medial, fasciculus gracilis. And the medial lemniscus is a tract of white matter. First order neuron goes in the dorsal root. Ipsilaterally projects up the dorsal column. Then it terminates in the medulla, where it lands in the nucleus matching the dorsal column. Second order neuron starts in the medulla. Decussates and ascends via the medial lemniscus up through the cerebrum into the thalamus, where the VPL of the thalamus serves as its last stop. Third order neuron starts in the VPL through the internal capsule, which is just white matter. Then out it comes and synapses on the brain, on the post-central gyrus of the parietal lobe. Primary somatosensory cortex, that is where this info finally ends up, responding to touch, vibes, and proprioception. The mechanoreceptors got the job done. DCML.
Well, I think that's fantastic. I'm sure many of you can do the same and even better. But I do thank our friend for being bold enough to put this video and make this available for all of us to see.